Good day, folks. I would like to talk to you about a circuit representation of the quantum cells. As I was saying last night when I went live, I couldn't sleep, so I was up most of the night trying to, figure out what was going on, especially after I randomly hooked up my pulse generator to it. So I was able to see a continuous action of that without having to trigger it myself and take more readings and further analyze what's going on. And everything from my previous explanation of the regauging and that of the effects of the quantum cells is still valid, but the second half, the full explanation, I was able to get to the bottom of it. And one long story short, what's going on is we're creating a very interesting variant of a relaxation oscillator, taking advantage of the self-capacitance properties of these cells. So let me explain basically what was going on when I pulsed this thing. So here's my scope here. So I send this thing a negative pulse, we'll say 10%. And then on the output I get something like this. And a little bit of ringing here. And I'm going, isn't that interesting? So I said, what happens when I pulse the plus with the plus and the negative with the negative? Like one would think so, right? Well, this is what happens. Same pulse on the positive side, but then what I get on the negative is like a tiny little blurb. What's that? Okay, so after thinking about it, you're still taking advantage of the capacitor. If you ring the capacitor just right, it will oscillate, but not on its own. You see, to create a basic relaxation oscillator, you need basically a resistor, usually something that has a bit of negative resistance, Zener diodes, a few diodes, crystals and whatnot, and you can make very primitive tunnel diodes is another one. And you can make fancy, very basic, interesting relaxation oscillators. But just, having a capacitor here on its own and just sending a pulse like that isn't going to give you any kind of oscillations, right? Because it's an open loop system here. So you're charging the capacitor, it goes up to whatever you give it, and then remains there unless you discharge it. So you don't notice any of this stuff going on. So if you're trying to build a very basic one anyways, the representation of what's going on in the cell would be you would have this C1 here. So let's try and build it like it'd be enclosed in the cell, okay? So the cell is acting as C1. And then you got your electrodes here, which is your plus over here and your minus over there going into the cell. Well, in here, it's going to be very high value, but this is part intentional with the copper oxide to make it partially conductive. So you're going to have a resistance value there. It's probably something crazy like 1 mega ohm or more, but there is going to be a resistance there. So now, if there's a resistance there, and we charge this capacitor, let's say at 9 volts, we bring this up to 9 volts, and what happens once we reach the peak and we let go? Well, the built-in resistance, very much like a protective resistor when you charge a capacitor, will slowly drain that back down. So essentially, this is what it's doing, but instead of going down to 0, it'll go back down to the standing voltage of the electrodes, which is about 1.2-ish, depending on how it works. So that's the first unusual thing, is it doesn't go to quote-unquote 0. It's got a positive standing voltage of 1.2. But that 1.2 is DC. So we don't see it on the scope. It appears as flat, unless I make, but looking at the AC waveform, we're not going to notice that because the standing DC voltage is always there. It doesn't really move unless they're minus the minor fluctuations, but all in all, it's a stable 1.2 volt DC. So here we have this condition where we send it a pulse. It basically does this thing, and it's negative polarity, and then you end up having, and then maybe a few, and then like that. So now that we see what's going on, it would explain why it only works in one polarity more than the other, because one is going against the natural voltage of the capacitor and basically just using as a regular capacitor, no enhancements. And it's very minor, very small, so there's not a lot of, but there is. So this is basically the effect of the parasitic capacitor. What you're getting here is a displacement pulse as it loads. So you're actually seeing the discharge curve appear as an AC waveform as it's doing that displacement, which is fine. Displacement current is great. This is what we're trying to go after, folks, because basically it's simulated AC. We can work with that. So, knowing what's going on here, what we can do is what I did last night. I hooked up a switch to this and I pulsed it in reverse, and sure enough what I observed was very well this kind of thing going on. And on and on and on, it goes like that. So I was able to further analyze that, oh, this is a kind of very interesting variant of a relaxation oscillator, but we're utilizing displacement currents instead of that balancing act. So that's why when the polarity is right, you're getting the voltage, the ring of the spike at the opposite polarity, the equalization and the cell working with it. So it kind of like, it's an amplified pulse for sure, but the energy, what I'm trying to say, doesn't come from nowhere. It's being added to the natural potential of the spike. So when you get that momentarily pulse, as its internal resistance is helping to rebalance that, as it discharges, creates a displacement current internally. And then essentially it'll flip its polarity back on its own to its 1.2 positive voltage here. So understanding what kind of mechanism is going on here, the cell is sweet because it has all this stuff built into it. But once we understand what's going on, there's no reason why we can't include this in the circuitry somehow and take advantage of pure displacement currents for an efficient kind of power supply, let's say, without needing to go too complicated with traditional reactive power supplies where your capacitive values, your transformer values, and everything else, and the circuit has to be in that sweet spot, or else you may actually end up being less efficient than using a traditional version, right? So there are sweet spots, but the more, Don Smith-ish you get into it, the more complicated it gets, but the reward, obvious at the end. I don't have to go into that. But to start and to understand the concept in its basic terms, this is very helpful into seeing how these cells work, inspired me to try and figure out a circuit representation. So let's try and do a circuit representation. All right, folks, here's the closest circuit approximation that I could come up with that would probably, with some fine-tuning, would give you similar effects. So basically we try and simulate the cells slow but self-regaging capabilities of around 1.5 volts. We send this through a rectifier. The 47K resistor, we'll probably have to fine-tune this. It's just to show you the conceptual idea here. What you want to do is this kind of a setup being relaxation-like. You can't have your inputs too hot, so this allows us to limit how fast our system could re-gauge, very similar to how the cells take a moment, So as much as we can to simulate the automatic re-gauging of the standing voltage. So this charges a 1 UF capacitor, which simulates the capacitive into our quantum cell here. And what we have here is we also have a 1 Hertz 10% just to start with, 9 volts like I was simulating with my battery, with the help of a diode here to help with feedback, which we keep triggering the capacitor at the reverse of the standing voltage. Now what we're going to do is we send the output of the capacitor to another full bridge rectifier, but we load it. So this 1 mega ohm resistor would simulate the high resistance value of the solid state electrolyte, which would essentially be the closest equivalent to the discharging capacitor, the discharging resistor when you charge a capacitor. So during the charge time there's voltage, but there's just within the moment. So it's thanks to this discharging capacitor that we can simulate the built-in effect of what the cell does when you pulse it in reverse. So this allows us essentially to create a pure displacement current generated wave as far as the output would be concerned, The reason it's AC is it's because it's of the DC displacement caused by this, because we have a base voltage which gives us a base voltage, we're not going back to zero, so it's always going to want to fight with that. So what you're getting here is the displacement current, which is very good, something we really want to tap into. So here's how it would look like at the output here. And you'd end up with your trigger, and then your output, your trigger, and then your output, but all because it's on the rectifier here as a DC. So you could, if you were to zoom out of this, you'd end up having, with a steep curve here, something that looks a lot like a regular sine wave, which is great because that equals current, folks. And it also allows us to recover part of the displacement current of your input trigger as well. So I don't know if some would consider this the CEMF, but it allows you to capture the front and get back the back, but displacement current wise. So we're not tapping directly into the input sources per se. We're creating, thanks to the capacitive, a base voltage, and because of the reverse spike, it wants to equalize because it's got that continuous, which we're simulating our cell feature. So of course nature wants to balance that potential difference, and it's that balance that gives you the displacement current for a moment, giving you these waveforms. So yeah, obviously I'm putting 1 UF, 1 mega ohm. We'd have to experiment with the circuit and the values, but what I'm getting at, folks, is I'm pretty convinced that we can simulate the behaviors of these cells in a circuit if we really wanted to, leading to very efficient, maybe even over unity, looking at the displacement current as a separate system here that we don't normally tap into. So this is definitely a possibility leading into the Don Smith-ish kind of systems. And what's fascinating with this is we're not dependent too much on any resonant fancy coils, all that stuff that usually confuses the smithereens out of everyone, So there you have it. I hope this circuit representation is a good one anyways of what the cell is doing on its own. So with that said, I think with circuitry we can simulate just about everything if we do it right. So nothing says you can stop here. Why not include some magnetics in that, put some magnetic amplifiers and keep it going, right? Stack it up. As long as you know what you're doing, you can work with that. So I'll leave it at that, and I hope it helps, folks. Thank you very much for watching and your support and everything.